Okay, so basically looking at your data, okay, part 1 is simulating the reaction, reactants going to products, and if you notice, what else is different about this little thing right there? Yeah, the arrow is going both ways, right? It's not just going in the forward direction. And so this whole lab is about equilibrium, where we're going to be seeing a reversible reaction. So things can go either in the forward direction or the reverse reaction, whatever it's needing to do to find this equilibrium, okay? All right, so if this is what it's representing, the volume in cylinder 1, the one that had the water in it to begin with, who do you think it represented, the reactants or the products? The what? I think someone said it.
The reactants?
The reactants is right, yeah. Sorry, hold on. All right, there we go. All right. Right, so we got our reactants, or letter A. Okay? Because basically we started with something, and what did our numbers show us? What were they doing as you move across?
Going down.
They're going down, exactly. Okay? And so, and then in the other one, we have something that's starting at 0 and eventually gaining stuff, right? So what is that one representing? The products, right? Because typically we don't start with anything to begin with. And then we continue on, and then you'll have products at the end. So in terms of a forward reaction or a reverse reaction, which one was shown when we transferred water from 1 to 2? The forward. And then obviously 2 to 1 would be our reverse. Okay? And then the diameter of the straws. What are you guys thinking on that? It could be a couple things. Right, so obviously the bigger straw collected more water that was able to move versus the little straw, right? So if we think about our table number 2 and the difference between those, so what does that tell you? Right, I want you to think about like a balanced chemical reaction. What are things that we have to consider that maybe is different? I wouldn't go with the charges necessarily. What other awkward numbers do we have to put on those? The coefficients, right? Could it represent your different mole ratios? Right? So let's just exaggerate and say that the big diameter straw was double that of the small straw, right? So it was moving twice as much every single time you did a transfer. That's what we're thinking here, right? It could also be something like the concentrations. Actually, don't write concentrations. Don't write that one. We'll leave that one off. Just talk about the mole ratio, because it really just has to do with the transfer itself. We'll come back to concentrations later. All right. So then your homework this weekend was to take that data and you needed to graph it on here. And so for the most part, you ended with graphs that looked like this, and some of y'all's didn't cross, some of them did cross. This one for sure crossed, so that was cool. But in the end, all of them did this thing where they just evened out, right? You guys saw that. And you saw that this one always started from 0 and it went up, this one started from 50 and it went down, right? So in the end, that's kind of the general outline of both of these graphs. And I showed you that so that when we go to analyze them a little bit later, you at least have this to fall back on, that it has to do with the fact that there was movement happening the whole time. So that leads us to question number 3 right here. It says, what are 2 important defining characteristics of dynamic equilibrium? So if this thing was showing dynamic equilibrium, you know that you were transferring the whole time, right? So movement was constantly happening. Okay? And for my people who continued their graph the whole data table like they were supposed to, would have seen that even with that movement, what you started doing was not seeing a change anymore, right? We started seeing that the numbers were starting to stay consistent, okay? Maybe not equal to each other, but consistent. So movement was still happening and concentrations were staying the same. We'll just put concentrations for now. Okay? How can you tell by looking at your graph when equilibrium was established? What did your graph do? It was after they crossed each other, but what did they do? They flattened out, right? So they all just went flat. So we could say zero slope. Do you guys know what that means if I say zero slope? Yeah. All right, so if you were to calculate it, it would literally come out to be 0. All right, so zero slope, so a flat line. Okay, a horizontal line. And then number 4, unfortunately, I think with everyone's different processes and different groups, spilling waters and all that good stuff, I don't think you're going to be able to answer number 4. So one thing I just want to point out, though, is that it's talking about which one looked faster when the concentrations of the reactants and products are equal. So what we're talking about here is that you'd look at a steeper slope. Okay? And eventually we'll come back to that. All right. All right. So when we're talking about equilibrium, you can kind of see on this image that it looks like kind of an image that you probably saw back in biology, where you had a semi-permeable membrane, right? And so things were able to flow in and out of like cells. I think that was where you guys saw it, right? Yeah? Yeah, osmosis, exactly. All right, so until eventually they reached this point of equilibrium, or you guys had homeostasis and all that good stuff, right? You guys remember that? Do we see that I teach chemistry, not biology? Yeah, okay. All right, so anyway, so that's all that this is showing you, is that that's what we're reaching, is that over time, eventually things have to reach this balance, okay? Everything wants to get to balance, okay? And that's just a general rule in science. So equilibrium is just the state where the concentrations of all the reactants and products remain constant with time. So after time passes, concentrations just start leveling out. They just stop, okay? But as you guys could see, transfers were still happening. There was still dynamic movement going on, okay? All right, so reactants make products while products make reactants, okay? So reactants make products is like a forward. Products make reactants is a reverse, okay? The rate of change is equal in each direction. Opposing processes are in balance. Chemical equilibrium means that the rate of the forward reaction is equal to a rate of the reverse. You will be seeing this a lot in your notes, okay? Because it's all about rates being the same. All right. So reactions are reversible. This is indicated by your double arrows. Okay? So you'll see me draw it like that. I do half arrows, kind of like when we were doing our orbital notation. You can also just do that. That's not a problem. I've seen it both ways. So. All right, we kind of already talked about the word dynamic, but dynamic was just meaning movement, right? So I think in your English classes you learn about like dynamic versus static characters and stuff like that. One changes, the other one kind of stays the same, usually. Yeah, do I got that right? Yeah. Okay, cool. Maybe I just need to stick with chemistry. All right. So the forward-backward indicates that the reaction is proceeding in the forward and reverse direction, and once the equilibrium is established, the rate of each direction is equal. This keeps concentrations of the reactants and products equal. Or you can also just say stable, because I don't want you to think that they're equal to each other, just their rates. Okay? All right.
Bless you.
Bless you.
Thank you.
Bless you. All right. So this is the graphs that you guys already drew. So things that you need to be ready to answer. What is the top line representing? Who in a reaction is the top line representing? Reactants. I know. Okay, the reactants. So would that be the forward reaction or the reverse reaction? This would be the forward, right? Because hopefully you have a lot of reactants to begin with, and then the reactants start to run out, right? I mean, we don't completely run out, but you got that. All right. And then on the other one, the bottom line, who's that one representing? This will be your products. So therefore, the reverse reaction. Okay? So this is your product starting from 0. Actually, no, I shouldn't say reverse reaction. I'm so sorry, you guys. I'm blanking out. Because this is showing your products making, right? So both of these are showing that. All right. And then can you tell me where equilibrium is established? I know it's labeled, but could you look at this without that little label on there and tell me where it reaches equilibrium? It's when both the graphs do what? Flatten out, right? So it's showing this little line right here, okay, as your equilibrium point. All right. Okay, so at equilibrium, the concentration of all your reactants and products stays constant. It seems as if nothing is happening because the macroscopic properties, which are those that we can see, so macroscopic are like big things, okay, do not change. However, at the microscopic level, okay, there is continual change. All right, so all that this is showing is another representation of the graph. Will you be able to answer those questions? Products, reactants, equilibrium. Yes or no? Yes, okay, good. All right, so at equilibrium, rates will be equal. And this is actually a whole different unit when we're talking about rates, and that's going to be kinetics, okay? When we're talking about rates, what we're looking at, because you can see this graph is a little different, right? This is where they are hitting each other. This is not a concentration versus time graph. So this isn't showing the same thing that we were looking at before, okay? What this is showing is your rates equaling out. And when I say a rate, we use these funny little symbols like this. So this is saying change in concentration with change in time. And have I used the delta symbols in here very much? The little triangles? Okay, so you'll see them a ton when you go to physics. Delta just means final minus initial. It's just a way to put in values. You have to have two concentrations, so a final concentration and initial. And you have to have a final time, and usually your initial time is 0, right? And so, so that's all that that's showing is a change in concentration over change in time. All right, these next 5 little bullet points, those are going to be something that you probably want to study, okay? So when you're talking about chemical equilibrium or a system at equilibrium, it has to be a closed system. So in our labs previously where we had like an open beaker that you guys were analyzing, was that a closed system necessarily? No, okay. So when you really want to see the true effects of it, you got to look at it that way. Or you have to take into account, like we did, hey, whatever mass is missing obviously went to the room, so you could subtract the mass that was missing, and that was the gas, right? And you guys can do those. So you can make assumptions, all right? But you have to treat it as a closed system. Macroscopic properties are constant. Okay, and concentrations of reactants and products stay constant. But, as you guys saw with your straws, continual microscopic changes are occurring, or microscopic change occurs between the reactants and your products. The rate of forward reaction equals your rate of reverse, or backwards. Okay? And just like I keep saying, constant does not mean that they're equal to each other. It means that they're just not changing. All right, this next little section I'm going to have you read tomorrow before we start up. You're going to do a short little pogle over Le Chatelier's principle. And this will kind of lead you into it. It'll give you another way of thinking of it, and then that'll give you another example, and you'll get it. I promise. So we'll look at that tomorrow. So now everybody should be changing the page for sure. Go to the next page. All right. So your position of K depends on three main factors. Now, when I say the position of K, what that means is that where equilibrium is established. Okay, it can be equilibrium can be considered somewhere where a forward reaction is taking place a little bit. Products are being built a little bit more than the reactants are, but that could still be at equilibrium. And then the reverse could be true, or they could just truly be totally equal. All right. And so you're going to be hearing me say favors this side or favors that side, or proceeds to the left, proceeds to the right, things like that, and just roll with it for now, okay? But anyway, your K depends on initial concentrations, energies, and your organization of reactants and products. The bottom two little bullet points there, we're going to deal with more in thermo. The first part we will be dealing with, and this is something that we kind of saw before your guys' tests last week, where I was talking about the collisions. That's how you make a reaction go. It's the fact that you want all these molecules to just hit each other so that you're forming whatever you're trying to form or break apart. Okay? The equilibrium expression is known as, and you will never hear me say it, but I want you to write it down so that you have it. Okay? As law of mass action. Law of mass action. Sorry. It's M-A-S-S. All right. Okay, and in your law of mass action, or when you're finding out your equilibrium constant, okay, which is just your KEQ, just put K. There's tons of different Ks, by the way. There's like a KA, KB, KW, KSP, KP, KC, KEQ. There's tons of Ks. So it's okay if you just use a general K. Okay, got it. See what it is? Never mind. Okay, not funny. You're right. All right. Okay. But anyway, these Ks are temperature dependent, and that might not be super important to y'all right now. But for my AP kids, they have to refer to this big 3-page thing in their book where it has a list of all these K values, right? And it's temperature dependent. So the minute that temperature changes, they can't listen to those numbers anymore. All right, it changes a little bit. So you gotta consider temperature definitely when you're looking at these K values. Here you go. So your equilibrium expression or your equilibrium constant. I'm going to put expression. Okay. For the general reaction, and you guys see little A plus B equals C plus D, all right? So you guys can kind of look at the formula over here, okay? So if you notice, generally, who is on the top out of your reaction? Well, it's C and D, but what are those guys called? Those are the products, right? So it's always going to be your products over your reactants, and that's the general outline of these, all right? So it's going to be products over reactants, and what do you notice? What are those little letters representing? Coefficients, and if you notice, we're making them be little exponents. Do you see that? And so that's where your mole ratio is going to come into play again, okay? All right, so your product concentrations appear in the numerator. And the reactant concentrations in the denominator. Okay, each concentration is raised to the power of its coefficient. All right, but in the end, the general outline is K is equal to concentrations of products over concentrations of reactants to their coefficients. Okay? So as you can see, I keep using brackets, and you keep seeing brackets. Brackets just mean that concentration, molarity. Okay? I'm having a really hard time writing today. So it means molarity. All right? And then you can have concentration of different gases, but for pressures, what I want you to remember for pressures is I want you to use parentheses, not brackets. There you go. Okay? So for pressures, put things in parentheses because those brackets specifically mean concentration, or they specifically mean molarity. And when we're dealing with pressures, we're dealing with some stuff like atmospheres, torr, you'll hear a bunch of other ones, kilopascals, okay? So just keep that in mind. I won't put too much pressure stuff on here because you guys haven't done gas laws yet.
Wait, Miss, I have a question.
Yes.
I saw this video with this guy, like, they were, like, really deep.
All right, so when we're looking at these K values, okay, so if you have a K value that's greater than 1, looking at your general outline right there, right, who does it mean you have more of, products or reactants? Wait, what? If I have something that's greater than 1, if K is equal to greater than 1, do I have more products or reactants? Products, yeah, okay, just a little fraction math there, okay, so that means that if you have a K greater than 1, it favors your products. Okay? If it's favoring something, it means it's making more of that. Okay? And if I'm making more of that, that means that I favor the forward reaction. So I just want you to put an arrow showing the forward reaction. If you have K being equal to 1, means that it's already at equilibrium at those given conditions. If I have something that's less than 1, it means that it's favoring your reactants at equilibrium. Okay? All right. So now you guys are going to practice writing some of these, then I'll tell you what your homework is and we're done. Okay? So homogeneous equilibrium just means physical states of your reactants and products are the same. Just like a homogeneous mixture means it looks uniform throughout or the same throughout. All right, so looking at our example, we have some hydrogen gas, some iodine gas, and then it's creating hydrogen iodide, okay? So if I wanted my equilibrium expression, and we're going to just fix that. There you go. Give it a double arrow. You should have a double arrow if you're going to put something into an equilibrium expression. All right. So looking at this, you can see that we put our products on the top. So with the hydrogen iodide with its exponent of a 2, and then you see that the reactants are on the bottom, right? So looking at our example down here, we have NH3, O2, NO2, H2O. First of all, what kind of reaction is this? What type of reaction? There's some oxygen and water, and we're making some sort of a dioxide.
Combustion?
Yeah, it is. It's combustion. Okay, but if you notice, instead of a carbon, yeah, we're dealing with a nitrogen-hydrogen combination. Okay, all right. So when we go to write this, who goes in my first set of brackets?
Oh, your reactants.
No.
Your products.
Yep. So I think some people are saying NO2. Okay. So NO2, does it have a power? To the 4th. Good. Okay. And then my other set of brackets, we'll put H2O. Does that have a power? 6. Good. all over. Now we're going to put our reactants on the bottom. So NH3 to the 4th power and O2 to the 7th power. Okay, and the next step from this would be me giving you values and you putting it into all those little brackets and taking it to those powers. Okay, that'll be our next step, but not yet. All right, so that's it. Easy, right? Not too bad. Okay. Heterogeneous equilibrium just means that you have different states of matter going on. Okay, and that changes a little bit. Okay, and this is actually more common to have that. All right, so here you guys see that we have some solid carbon, some gaseous water, so water vapor. We have carbon monoxide and hydrogen gas. Okay, if you look at the equilibrium expression, who is it leaving out? Who's it leaving out? Carbon, right. What state of matter is carbon? He's a solid, all right? And so we leave out solids, okay? There's a set of rules when you're dealing with different states of matter, okay? And they're right here down below. So first you've got pure solids aren't going to appear in it. When I say pure, it doesn't mean that it has to just be one element. It could be sodium chloride solid. You would not include it. That is a pure compound, okay? So pure solids, so just solids. Anytime you see that, leave them out. Pure liquids, anything that has a cursive L. Our typical one is obviously water, right? And that's listed next. So water as a liquid, or if you have water as a reactant, which will be important to you when you get to our KSP, which is solubility rules. We'll look at what those are going to be represented with, because we typically would put something into water, right? You would leave out water, plus it's a liquid. And then we'll also see that for acids and bases in the next unit, okay? The whole reason we do this is because they don't affect it. We take them as being equal to 1. Okay? So if we divide by 1 or multiply by 1, it doesn't really affect it. All right, so you got to remember this for the next side. So look at the next page, whether it's the same or not. There you go. All right, so looking at this, it says, write the equilibrium expression for the following processes. But first we have to have balanced equations. So the first one says the decomposition of solid phosphorus pentachloride that turns into liquid phosphorus trichloride and chlorine gas. So phosphorus pentachloride, how do we write that? What's phosphorus? P. How do I do pentachloride? Cl5. Good. Do we have to crisscross charges? No. This is a molecular compound. There's no metal involved, right? So there's no ionic substances. So you just listen to your prefixes and write it out. So phosphorus pentachloride. We're going to give ourselves a little double arrows. To liquid phosphorus trichloride. So phosphorus trichloride would be what? P. Cl3. Good. Tri means 3. And this is a liquid. I should have put a solid over here. Sorry, my bad. Plus chlorine gas. So just Cl. Just Cl? 2. There we go. All right. And this is a gas because it's part of the diatomics. Yep. Okay. All right. So looking here, what would be my expression? Be careful. I heard you guys say Cl2. Is that it? Yeah. Because what do I have here? What's this? That's a liquid. What's this? Solid. Do we include either of those? No. Okay. So this one is just straight up the only one that's gaseous. So it's only dependent upon the concentration of the chlorine gas. Okay. So if I were wanting to shift equilibrium, which that you'll go into tomorrow with Le Chatelier's principle, the only thing you could really mess with here is your chlorine gas. You could add some more or take some away. Okay. All right. Your blue solid copper 2 sulfate pentahydrate. Woo. What does that one sound like? It's your favorite problem in the whole wide world. We had warm-ups on him.
Oh, CuSO4.
So we have CuSO4 for sure. How do I do the pentahydrate? This is the one with the crucible and the how much water is driven off. And you guys remember all that? So how do we write the formulas? The dot, yeah. We're going to put a dot, and we would go pentahydrate. Ooh, I should have put it to 5 first, sorry. Pentahydrate. Good. Okay, so we have that. We're going to put it into some heat to drive off some water. Just put your equilibrium arrows. And so we're going to form some water vapor, right? Might be floating in the air, but it's water vapor. And then solid copper to sulfate. And then obviously you guys know from your lab, what was the beginning step? What was the reactants? What state of matter? Solid. Okay, so looking at this, what's your expression? Yep, but we're going to put H2O in the brackets, and where does the 5 go? To the top. Yep. All right, and that's it. Okay. Okay, so go ahead and you're going to have to flip a couple pages, so just kind of look at where I'm going to take it to, and you can see right there. All right, so once you found this page, okay, as a little description so you can read that on your own, but what I'm wanting you to do for homework is example 1. So it gives you 3 little expressions, or 3 balanced equations, and I want the equilibrium constant expressions. Couple hints. Some of these have charges on it. So you see this like Cl2, that's in letter B. I'm sorry, not Cl2, woo, Cl, but it has a little minus sign. Make sure you include charges, and then you would take it to the second power. Okay, so make sure you don't forget charges. I will explain to you tomorrow what that is all about. It's something to do with net ionic equations that we kind of skipped over a little bit. So I want you to do those 3. And then I would like to see you attempt example 2. This is actually plugging in some numbers. Or at the very least, tell me what all the concentrations are. So remember, concentration is moles over liters, right? And so they give you a bunch of moles. You need to put it in over 12 liters and figure out all of your concentrations, and then we'll deal with it tomorrow. Okay? So that's it.